Okay, it's 8:15. So, good morning, everybody. So, I'm your lecturer for general physics. My name is Tim Burns. And so, I'm going to tell you a little bit just about the course first. Just basically take you through the syllabus and answer any questions that you may have. So, okay, so let's just go through the syllabus first. Well, as you know, the location is here. There are my office hours. All this information is on the website, so you can look at that later. You don't have to take notes. Your recitation instructor will be Junheng Shu. He's just right at the back there. I'll ask you to come up and explain the homework a bit later, yeah. And also your learning assistant is also in the corner there, Shanglin Yang. Okay, so as I said, the course website is just on Brightspace. I think many of you have already found it. A lot of the information of the course will be there. I'll be mainly using it just to upload some sort of resource materials and things like that. So I'm not going to be really intensively using it to submit all your assignments and so forth. My office is in room 1113. You can always reach me by email, of course, but my office hours are Tuesday 4 to 6. Oh, I didn't write the room number in this one, but it's room 1200. And so actually this is my research group meeting, so you might see some other students there, but don't worry about that. Just come in and ask me any questions. Okay, or just find me after the lecture. It's probably the most surefire way to catch me. Okay, and the textbook is Halliday, Resnick, Walker. I used these slides from a couple of years ago. Is there a newer edition now, or is this still the latest edition? Still the latest. Okay, great. Okay. Cool. All right. So physics hasn't changed very much. Okay. So yeah, we'll use this textbook quite a lot in this course. Basically, I'll be very closely following the first 10 or so chapters plus 3 more chapters doing thermodynamics. So you will definitely need this textbook. All the homework questions will be out of it, and basically, for further details, you really should kind of read this book. However, I didn't make it a required textbook because it's an extremely expensive book, and it's just a recommended book for the purpose of the course. But that's not to say that you will not need it. You'll definitely need the book somehow. So I'm leaving it up to you of how to get the book. Okay, and for the course goals, so, basically what I want you to sort of get out of this course is really kind of how to sort of think like a physicist. So it's not so much necessarily that, you're going to need like Newton's laws and thermodynamics in the future. However, physicists, the kind of way of thinking of a physicist is to kind of break things down to their most essential principles and then kind of find the core of sort of the truth of the matter, so to speak, and then kind of work your way up from there. So it's really kind of a ground up type of approach. So if you could sort of get a sense of how sort of physicists think, I think this would be probably the bigger aim for the course. So, a lot of you may have already seen some of this material, but what I want to encourage in this course is to kind of maybe use these ideas, think out of the box, and kind of try and apply them to real life. And I'll get onto that regarding the assignments in a minute. So, as for the actual kind of material, so this is, it's obviously kind of a freshman level physics course, so we will go through kind of the most basic and most famous types of results in physics. So this is things like measurement, motion in a straight line, vectors, motion in 2 and 3 dimensions, so forces, so this is things like Newton's laws, kinetic energy, potential energy, conservation of momentum. I think actually we tend to often not do so much rotation. That's time depending on the course. And then these 3 chapters on thermodynamics. So this is concepts of temperature and kinetic theory of gases, second law of thermodynamics, and entropy. So I think, a lot of you may have actually seen this material before, right? A lot of this material you might have actually seen already in high school. So, what I encourage you is actually, if this material actually looks maybe too easy for you and you've done it all before, then there's also kind of the parallel class, which is FOS physics, I think. And they do more advanced materials there. If you've done all this material before and you're going to be bored in this course, then I encourage you to also consider swapping to that other class. I say this now because I don't want you to all sort of feel like you're just covering all the same material. But some of you may have not covered this material, so this is why we will go through this stuff. Okay, and right, homework. So maybe Junheng could explain this one. You can just.
Basically, what I want to say is about homework on this slide actually.
Yep.
So just to let you know this schedule, because during the semester, most important thing is the homework, right? And so the homework will be problems will be updated to the bright space, and the bright space, right? So every Thursday evening, after the second course, so second lecture in the week, and then will be collected. You will be bring them here on Tuesday's class, and I will be collecting them after the class on Tuesday, and that's also the deadline, But of course, some exceptions could be made, but not too often. And there will be penalty, like if you continuously only submit the homework, after Tuesday, and also the homework will be graded during the weekdays, and then I will be explaining them on the Friday during the recitation, and then will be returned to you on recitation, and you may ask me more questions after recitation or during my office hour. Well, I think it's the same as Teams, and so that's basically it. So more details about the requirements for homework, I think I will just explain on the recitation, not here. So
okay. Okay. All right. Thank you. Okay, and learning assistant. So Shanglin, you want to say a few words? Yeah. Okay.
Okay, good morning everyone. My name is Yang Shangling. You can call me Shangling. I'm a sophomore 4th student in NYU Shanghai. And the last year I took the General Physics 1, and this semester I will be the learning assistant for this course. Basically, a learning assistant will help you to better learn this class. If you have any confusion or difficulties during the study, you can make appointments with me through the ARC website. My available office hour is on Monday and Wednesday from 11:30 a.m. to 1 p.m. If you find none of these time slots is suitable for you, you are welcome. You feel free to contact with me with the email sy3112. And I think I have already sent a greeting message to all of you guys yesterday. And for the freshmen who may not familiar with the ARC, ARC refers to the Academic Resource Center on the 5th floor in this academic building. And if you don't know how to make an appointment online, you can just directly walk in the ARC and find me, and I will teach you how to make your first appointment with a learning assistant. And the review session will be held on Friday from 4 p.m. to 5 p.m. One thing I should point out is that both the office hours and the review session is not mandatory. I mean, it only serves for those who have difficulties or problems in your study, so you don't need to go here every time. Okay, for our convenience, I also set up a WeChat group I stick the QR code here. You are welcome to join our WeChat group after the class is over. I will send the information both through the WeChat and the email. Okay, thank you.
Oh, sorry. Actually, I haven't taught this course in a couple of years. So the review session means what you're actually just going to go through the material, like.
I just review what professor you have taught in
so
this
that's
week.
like a mini class.
Yeah,
voluntary mini class. I see. Okay.
Voluntary.
And then the other ones by appointment. You can sort of sit one-on-one with. Okay, I see. Okay. All right. That's great. Okay. All right. Okay. And the assignment. So maybe firstly I should tell you kind of the breakdown, right? Okay. So the breakdown of the marks are like this. So homework is 15%, and so I think we just divide each homework equally for the 15%. The exams, midterm exam, final exam, these of course form the bulk of the marks, so they're the most important to get right, of course. And the quizzes, this is only 5%, but we have this because it's sort of like a practice midterm and a practice final. So I think we'll probably have 2 quizzes, and generally we'll have them a little bit before the midterm, and they're not weighted very highly, so you can, completely flunk them and then, adjust accordingly, right? So, so those are the quizzes, and assignment is 15%. So what is this assignment? So let me go back here now. So I like to do this because, in physics courses often you just have problem solving and exams and stuff like that, and then you never really sort of feel like you apply any of these concepts in a real world sense. Secondly, also, if you ever get onto doing sort of more advanced studies, like if you go to graduate school, or maybe if you, even become a researcher at a university or some institute, then the kind of science that you actually do is quite different to what you'd really do in textbooks, right? So when you're learning physics for the first time, you feel like physics is something where it's just like, you read some material, it's all very confusing, you do some problems, and it twists your mind around, and then you just got to, go through all these, questions forever and ever. But, real research is actually not really like that at all. Of course, there's no textbook, there's no, problem sets that some person has thought of. These are real problems that have to be solved because you want to actually do something, right? So if you want to achieve a particular task, you need to kind of work out how to solve these problems. And, that's actually what physics should really be all about. Doing kind of problems and stuff is sort of an artificial construct, if you like. So just to give you a bit of a taste of what it's kind of a little bit more like to actually do real science and to apply these ideas that we're talking about in a slightly more real world sense, we have these assignments. Okay, so I'm going to talk about the assignments in a little bit more detail in another lecture, because otherwise we'll just be talking about we won't be getting into the material. But these are kind of open-ended topics that you will investigate in groups, and because this is for NYU Shanghai at least, it's quite a large class. You'll be working in groups of 4, so there should be something like 8 groups or 9 groups. And you'll need to sort of do a presentation, but as a group. And so you'll prepare some PowerPoint slides and then present it to the rest of the class. And it doesn't have to be very long. It's just like about 10 minutes or so, the whole thing. We'll schedule these group presentations throughout the semester. So obviously some of you will be because there's 9 groups and we've only got 15 weeks. So some of you may already start to do this already in the next say a month or so. So we should we'll assign these groups probably already in the next week. And at the end, each person still has to write a report. So separately, even though you're working on the same topic, you'll write a report on each one of you. And so you will still be sort of individually assessed, although you're working as a group, so it's a bit hard to completely discriminate you all, but still there'll be some dependence upon how well your report is written. And the point of doing the presentation and then having the report at the end is because when you do the presentation, I don't really expect you to have completely sort of worked out the full problem. It can be sort of more work in progress, and of course, if you're presenting already, in a month or so, then you may have not made so much progress. But it does give you a bit of time for you to, for say, me to give you, and maybe everybody else in the class to give you some kind of feedback of like what kind of things would be interesting to look at. So basically, the presentation is going to be sort of a somewhat informal or incomplete work in progress type of situation for your project, and then the final report will be your final kind of conclusions, and that will be in written form. As for the topics, I'll talk about this in the lecture, but it will be a selection of like about 10 topics, which I think would be relatively interesting. So these are things like, I can't remember all the topics off the top of my head right now, but things like, explain how the Hyperloop concept might work, right? So there's several companies in the world that are trying to, do this Hyperloop kind of idea where you sort of build some tunnel and then you go through. It doesn't really make sense in terms of sort of energy and will it be really faster. There are all kinds of opinions on this. Some people say it's complete rubbish, and some people say it's the future of transport and so forth. So, and when you investigate these types of things, you want to sort of not just sort of just talk it up or just say your opinion, but kind of make it a little bit quantitative, right? So you want to sort of do some little calculation and try and sort of figure out, on your own terms of what you think, is the most important parts of the problem, and then apply your ideas and then come to your own conclusions. Okay, so it's like that. Okay, so hope that's not too daunting. I mean, the other good thing about this is actually doing presentations is a super important skill, right? So even if you go into academia or do research or anything like that, actually you've got to give presentations all the time. So this is also very good practice. Okay. Right, and the videos or lectures that you might have noticed, I've got all these cameras and stuff here. So I'm just uploading all this stuff. There's a YouTube site that you can find all this material. The main reason is because some of you are taking this course offline, through the pandemic, overseas and so forth. So all these videos will be uploaded. Actually, I need a bit of help with the video setup, so I'm going to ask somebody to help. And the reason why, and let me just explain the video setup a bit. But the problem why I have my own setup is the problem with these Zoom cameras is that that's great if you're just sitting and talking and you got PowerPoint slides. But as soon as you write on these boards, can't see anything. So that's why I got my own camera to record just the whiteboard. But the problem with that is that it doesn't automatically switch between the PowerPoint and then the whiteboard. So that kind of just has to be done by somebody. And very easy way. I got a Bluetooth keyboard here. and there's a button F1 when it says whiteboard. This will switch to whiteboard, right? And it'll record just whatever I'm doing on the whiteboard. So basically, when I'm scribbling something on the whiteboard, and I assign you to be the camera controller for the day, then could you just press F1 when I go to the whiteboard? That's all you have to do. Okay. All right. So your job there. Thank you. All right. This is now on. Okay, so we've already talked about that. Okay, and then various, fine print. So, of course, I expect people to attend lectures and recitations. So it's generally mandatory, but there is no participation mark. So, of course, it's not penalized in terms of your marks, but it still is mandatory. Of course, it's probably the best way to actually get value in terms of actually learning the material. I like also students to participate in class. So, if I'm just talking up here for an hour and 15 minutes and just everybody's asleep, it's not much fun for anybody, right? So, if you have any questions while I'm saying anything, if you find anything confusing, then, definitely stick your hand up or just shout out some questions, because if you find it confusing, then most probably at least, a bunch of other people in the class will also find something confusing. Now, ideally, you should also read the so the material that's coming up. Of course, if you read it beforehand, then you're going to be, of course, up to speed. And yes, and of course, same with the recitations. You're going to be given homework questions, and if you haven't, done the homework, then you're not going to know what's going on. Okay. Yeah, okay. So, okay, don't worry too much about this first one. Yes, in principle, any late work will be penalized by marks. So, if something's due by a certain date, then of course, please get it in on time. Otherwise, you may lose marks for it. And academic integrity is taken very seriously, so please do not do anything like plagiarism, cheating, etc. Okay, and in terms of the actual material, in terms of the material that we cover, this will not be to the T. I might change this around because every year proceeds slightly different pace. So I might have to skip, certain topics, or if we go through it fast, we might go add a topic or so. But probably around here is the most suspect region. Okay. Any questions? Okay. All right. Well, why don't we go around the class, and then you can say we can do a class introduction. So why don't we just go around the class, and then you can just say your name, what country you're from, and like what your major is. Okay? All right. You can go first.
Right. My name is Santiago. I'm from Mexico, and I'm a math major.
Okay, we can go this way.
I'm Tiffany. I'm from China. I'm an honors math major.
I'm Yifei Jiang, and I'm from China, Shanghai. I declared my major to be mathematics.
I'm Holly Wu, and what am I deciding? I'm from China.
My name is Daisy, and I'm from China. My intended major is business and finance.
I'm Sophia Xiu from Beijing, China, and I decided to major in neuroscience.
I'm Victoria, and my Chinese name is Entropy. I'm a freshman. I'm from China, and my 10th major is neuroscience.
Hello everyone, my name is Steve Liu. I'm from Shanghai, China. I plan to major in neuroscience.
My name is Sebastian, and from China, I'm a major in biology and finance.
My name is Helena, and my Chinese name is Hui. I'm from China, and I'm planning neuroscience as my major.
My name is Zhou Yu, and I'm from China. I plan to major in neuroscience.
My name is Jackson. I'm from China. I'm going to major in mathematics.
My name is Wu Yang. You can also call me Ruben. I'm from Beijing, China, and my major is physics and finance.
So I'm Patrick from China, and my major is math and data science.
My name is Ruben from the United States, and I'm planning to major in computer engineering.
I'm Johnny from China, and I'm an honors math major.
I'm from America, and
I'm Andrea from Colombia, and my major is biology.
I'm Carter from the US, and my major is chemistry.
Okay, so, all right, thanks. Nice to meet you all. All right. Okay. All right. So then, let's get started. So, chapter 1. So this is from chapter 1 in the textbook mainly. So it's about measurement. Basically, really, very fundamental stuff. And oh yeah, by the way, the slides will be. I'll upload them later. Often, a lot of you ask for the slides, so you won't need to try and copy down whatever I've got on the slides here. Okay. Okay, so, all right, so very basic stuff, but, so why do we need standards? Standards are basically, a system of units or system of way of measuring things such that we can communicate all our measurement results to each other. Ideally, obviously the best way is that everybody uses the same units overall, but of course due to historical reasons, some countries use slightly different standards, meters and feet or Celsius, Fahrenheit, these kind of things. But gradually I think as we're reaching sort of the global village, we have a kind of, everybody is gravitating towards, at least in the scientific community, the so-called SI units, right? So, a standard, we use standards, and a good standard are things that are firstly kind of invariable. So what I mean by invariable is that they don't change, right? So imagine if the meter is different every year. I mean, that would be ridiculous, right? It would be chaos. And a second thing, it should be kind of accessible, meaning that it shouldn't be something that is some, very obscure thing where it's very difficult to figure out what it is, right? So if it was like, okay, there's this thing called the meter, but nobody knows how long it really is, and you have to go to this special tomb somewhere in order to figure out what the meter was, that would also be ridiculous because it would just not be very convenient to use, right? So, we use standards, we sort of take it for granted really that, everybody knows what, say, a meter is, everybody has access to it, right? And units are, of course, a unique name that you assign to the particular standard. So, meter is the unit of length, and say Celsius as the unit of temperature, and so forth. Of course, each type of quantity has different units, right? But there's a lot of things that you could potentially measure, length and temperature are just two examples. So in principle, every time you measure something new with a different type of quantity, then there will be a new unit associated with it. So, you could invent some, strange kind of, units of, say, color or something like this. But often what we do is to kind of break down these types of units to their more sort of simpler kind of elementary components. So, for example, the unit for power, which is the energy per unit time, there is a unit for it called watts, of course, named after Mr. Watt, but you can break this down into some simpler quantities. And so there are some kind of fundamental quantities, and I don't even really know why there are this exact 7, but these were deemed to be the most fundamental of the fundamental quantities. And so generally when you break down a particular unit to its fundamental components, these are the ones that you use. Sort of, I don't know, some people, I suppose, decided that these were more fundamental than the other ones, I suppose because they are most commonly measured in some sense, right? So mass, length, time, temperature, as I mentioned, but moles, this is chemistry, it's the amount of substances, number of atoms essentially, electric currents, and luminous intensity. Okay, so we use scientific notation often because the numbers that we deal with tend to be often quite large. So if you measure certain quantities like the speed of light, it turns out to be really huge. So they're not really numbers that you can just write down easily. And so instead of writing down 9 digits here, you can often really it's just the first few significant figures that are important. So scientific notation where you write down the first few significant figures multiplied by some power of 10. This is quite a useful way to write down large numbers in general or very small numbers. Here's some big or small numbers, okay? And as you would be very familiar probably, there are all kinds of prefixes to account for the fact that, some numbers are very big, so your kilo, mega, giga, tera, peta, and so forth. Okay, yeah, and for the purpose of here, we're using giga like just exactly, for example, 10 to the 9. You might know that actually a gigabyte is not exactly 10 to the 9 bytes. It's some actual power of 2, which is not exactly 10 to the 9, but it's nearly 10 to the 9, so you just call it giga anyway. But for what we're talking about, we just always use giga to be exactly 10 to the 9. Okay, and if you want to change units, so you might also think, okay, this is such basic stuff. I know how to change units, but sometimes it can get confusing. And in fact, when you're actually doing some like science research, often people find that the units are the most confusing part of the calculation. So you're doing all this, advanced quantum mechanics, and you're doing some crazy calculation, and then you just can't work out what units to use because people use all these different units, and it's not often kind of intuitive how to actually calculate it because you're not used to looking at these numbers. Like things like minutes and hours, you have a very good sense that, I know that a minute is 60 seconds, so obviously if I have 5 minutes, I'm going to multiply 60 by 5, right? I'm not going to suddenly divide by 60. It's either multiplying or dividing, right? But sometimes if you're using some units that you're just not familiar with, then you just go, okay, am I supposed to multiply or divide? And then, this is where a lot of people just make a mistake, right? And then you just divide instead of multiply, and then you get some crazy number. So the way to kind of think about this is to just think of this in terms of, think of it like an algebraic variable, right? So this is a sort of a very simple example, but you perform the unit change as if you're doing some kind of algebraic step, right? So 1 minute, 60 seconds, so you just say a minute is some variable like X or something, and then seconds is like Y, right? And then if 1 hour is 60 minutes, then so then basically you kind of substitute the variables and then you work out the final result. So you can perform unit changes sort of algebraically, right? Okay, so we can talk about a couple of definitions of length. So the meter was defined in several different ways through the history of time. So when I think a bunch of French people, I think they were the first to try and find this or establish some kind of system of units, right, the SI units. And so in 1790, they said, okay, well, maybe we should define the meter to be some fraction of a distance from, say, the equator of the Earth to the North Pole, right? And people knew roughly the size of the Earth at that stage already, of course. So in order to make something, like so big, 1 meter, they said, okay, well, let's just divide, let's say you find the distance from the North Pole to the equator, and then just divide by 10 to the power of 7. And then let's call that our definition of a meter, okay? So, so what do you think the problems of a definition like that is? I can think of a couple. Yeah.
Well, you wrote it there, isn't it?
Yes. So it really depends upon which part, you go from, which path you go, do you go through Asia, Europe, North America. Any other problems?
How can you measure?
How can you measure? Yeah, I think so. Yeah, that's a yeah. I think that's another good reason. Yes. How do you measure? And how can someone kind of practically use that, right? So you can say, the people in France are like, okay, everybody, we've decided that the meter is, this length, right? And then you tell that to somebody in, in China or something like that. And they'll go, okay, well, that's great, but so what do you want us to do? You want us to measure this distance, like from here to the equator, and how are we going to do that? And so maybe the way to phrase that is that it's not very accessible, right? Like it's not something that you can kind of easily do and use, right? You have to just what you should be able to do is just based on some simple statement, kind of do some procedure so that you can establish it, right? It also, wouldn't work if you're telling this to aliens, right? So you're saying, yeah, so on our planet, so the distance from here to here, and they'll go, I don't know how big your planet is, but how do I know how big that is? Ideally, you want to just be able to give them a simple kind of explanation and then just based on that simple explanation, they should be able to get that definition, right? Okay, so they updated it. So this one, it's quite variable and not accessible. So they updated it like this. They went, okay, so we get this like really nice piece of metal. Doesn't expand very much, like how things get longer or shorter when you heat them up, right? So of course, if it expands or contracts too much, then your definition is going to be out of whack. So we have our sort of master 1 meter sample, and then that makes it at least not so variable. I mean, obviously anything still expands a little bit when you heat it up. So if you have a super hot day, then your definition of a meter is going to be. And in order to make it more accessible, so what they did was just to go around town and then just put in various places, places that said, okay, this is a meter, all right? And then so if you ever wanted to figure out what a meter is, then you find your local meter definition stone, and then you go out and you go, oh, okay, here, I got my piece of string, okay, I know that it's a meter now, and then you go back. What do you think the problems of this are? I mean, certainly an improvement over the first one, right? So, but where do you think, maybe another way to phrase it is, where do you think you can improve, or what do you think the issues that arise with this might be? Yeah.
Well, again, you gotta tell everybody, right?
Mm.
So you gotta kind of make more than just one. It's probably good.
Yes. Yeah, that's right. So, okay, so this is in Paris, but what if you're not in Paris, right? Okay, I don't know. Where's your local meter, reference point? If you say, oh, you've got to come to Paris to figure out what the meter is, okay, not very useful, right? Another problem is, it's not terribly accurate because you got the master rod, which might be pretty okay. You use some special metal that doesn't expand very much and so forth. But this one's just rock. So, well, on a hot day, it will be noticeably larger. Okay, so 1960, they said, okay, well, we're going to do this. So we're going to get, neon tubes, right? I mean, these days you obviously don't see them so much anymore, but neon tubes are like, you put neon in a tube, you put some voltage across it, and then it glows, in the case of neon, like a kind of an orangey color. Different gases do that as well, and they emit light in all different kinds of colors. So krypton, not quite sure why they used krypton specifically. Perhaps it's because I think maybe there's maybe it's more monochromatic than the other ones. I'm not really sure actually. So anybody knows, let me know. So you put kryptons, this particular type of gas, and then you put a voltage across it, and then you measure the light frequency, and then the light has a particular wavelength, and then you multiply by some factor to make it like 1 meter, right? So because the light that's coming off this has a very particular wavelength. This is why, being monochromatic, that means only one color comes off it, right? Most things, like if you just use this light, it'll be a mixture of so many different colors that you wouldn't really be able to tell, which light frequency to use because you just have so many colors. But this one, I think it's probably mainly like one color, monochromatic. And then you use that to define your meter. So that's not too bad, but I think that's already quite good. So the reason why this is quite good is because that you can just tell anybody. I mean, okay, it requires a little bit of technology, right? I mean, you need to be able to put tubes of, krypton, put a voltage across it, measure the wavelength, and then, have some wavelength measuring device that is, sufficiently accurate, and then so forth. But I mean, it's a big improvement over the last ones because that's pretty much all you need to know, right? You hope that they know what krypton is, right? So this would work with aliens or anybody, right? So you just tell the aliens, in a distant galaxy, you say, okay, so get krypton, 86 krypton. Hopefully they also have some technology to get 86 krypton. Put it in a tube, put a voltage, or measure the light coming across it, and then measure the wavelength, and then do that, right? I mean, okay, it does require a bit of technology, but in principle, it's all there, and anybody should be able to do it. It's not sounds very high tech, but actually none of these things that you need to do this are very high tech. I mean, making the tube, you got neon lights everywhere, right? And then actually measuring the wavelength, this is also pretty common these days. But they further improved this to 1983 definition. Probably, I think, because again, it's just a little bit more, I suppose, accurate in the end. And in this case, it's sort of similar type of idea. You define the meter by the length of the path traveled by a light in a vacuum during some time period. So basically, in this case, you get like a vacuum tube, and light travels at different speeds in air or in water or so forth. So it needs to be a vacuum so that we got the right speed, right? And as I'll mention in a minute, probably one of the best and most accurate things that we have in terms of measuring anything is actually time. We can measure time just so accurately that, I mean, you might think just like, wow, how do you measure this time? You've got to get it exactly that time. That looks really hard. But actually, just the clocks are so good that you can do that absolutely no problem. So this one does depend a little bit upon another technology of measuring time very accurately, but actually it turns out that's actually not a problem. So this one is the currently used definition of length. Right? Questions? Okay. All right. And so here we go with the definition of time. So 1 second is time taken by 9,192,631,777 oscillations of the light, of a light emitted by a cesium-133 atom. Okay, and so that's the definition, which seems like super abstract again. Something got to do with the light that comes off some particular atom. This is definitely beyond the course, but I was talking up how good clocks are, right? So you probably want to know how you measure time so accurately. Okay, so again, it goes beyond the course, but this is roughly how it works. Okay, so when you have a particular atom, atoms emit different frequencies, and actually, this is the same reason why neon lights, the one that I was just talking about, emit colors only at very specific wavelengths. It's because so this is where you press the button. Yeah. So an atom basically has particular sort of energy levels. Okay. So if you look at an atom, it turns out that when did that disappear? Sorry. Back. All right. An atom has particular energy levels, and it turns out that an energy of an atom is not kind of continuous. So, like what we'll learn later is that like a ball can have basically any energy. You throw it, has more energy, less energy, whatever. If you look at atoms, it turns out they can only have particular discrete energy levels. And basically what happens is that when you have these discrete energy levels, say an atom is in this state and it falls down to this state, then it loses this amount of energy, right? So there's some change in the energy. And basically the all right, focus this time. Then basically the light that comes off it depends upon whatever this energy change here is, right? And there's some formula. There's equals HF. H is just some constant. And F is the frequency of light. And so in a neon light, when you see that orange glow, what's actually happening is that the electricity that you're pumping into that gas is making the atom go into some state. And for various reasons, which I won't go into, there's one kind of energy transition that you see more. And so basically that energy turns out to be some orangey color, orange. So, but all atoms have this same effect. So if you have this particular cesium atom, then it turns out that tends to emit a particular frequency, and neon was some orangey color that's visible light, but this one turns out to be more like microwave frequency light. So this is more like the light that is coming out when you heat up your lunch in the microwave oven, right? So it's some kind of other frequency light. It's got longer wavelengths. Okay. And the reverse effect is that if you shine light on this one, on the atom, it will actually go up in energy, right? So it's just a reverse effect. So if this falls down, it will send out light. If you shine light on it, it will actually go up. So in an atomic clock, what you do is you send a bunch of these cesium atoms, and then you can measure like what level they're at. And these different levels, this is denoted in this diagram by the blue and the orange dots. So maybe like the higher level is the orange, and then the lower level is the blue. And then what you try and do is you try and just, you start off with atoms all in the lower level. So this thing just gets rid of all these atoms in the higher level. So you just got all the atoms coming in at the lower level, right? So all the atoms are like in this level here. down the bottom. Okay. And then when you shine this microwave frequency into it, as I said, what it does is to flip these atoms into this higher state here. Okay? But you got to get the frequency just right to do this. If you get the frequency wrong, it won't quite do it. Right? So if your frequency was like a little bit too low, they're not going to all make it there. Maybe like 90% will, but not all of them. If you overshoot, if you go a bit too high, then again, you won't quite get all of them in it. So to get it right spot on, so that all the atoms are in this higher level, you need to get this frequency dead accurate. So that's basically what this is doing. It's measuring it over here. It's making sure that all the atoms are in this orange level. If it's like too high or too low, you adjust it a little bit so it's just right. And then once you got that, you can get this microwave frequency like super accurately. This is like, what is that? That's like 10 digits of precision. So, and once you've got your, some microwave frequency that's like super accurate, that's basically your clock, because you've got some oscillator which is just ticking at a very precise frequency, right? So, okay, so it's, it looks very high, so it's not like a grandfather clock. It's clocking every, 1 second. Obviously, it's much higher than that. So it's ticking this many times per second, right? It's like ticking 9 billion times a second. But it doesn't matter that it's 9 billion, whatever. It just still is ticking like that, and it's ticking like that at extremely kind of precise frequency. So these types of clocks are accurate to 1 second in 6,000 years. So if you had this kind of clock, it would only go wrong by 1 second in 6,000 years. And they had this kind of technology already in the 1960s. Okay, so it's actually really old technology now. What people are trying to do now, same kind of idea, but just using optical light. So something more like in the optical visible frequencies. Same basic idea, but now you can get clocks that are accurate to something like, how many zeros are there here? 3, 4, 5, 6. Yeah, so 10 billion years. Do you know what the age of the universe is?
14 billion.
Yeah, 14 billion. It's only going wrong 1 second in the age of the whole universe. That's how good clocks are. And they're recently doing some crazy experiments these days where, so for example, this is so accurate now that you can actually start to think about measuring, Einstein gravitational redshift. What that means is that actually time is traveling a bit slower. Which way around was it? Is it slower when it's higher or slower when it's lower?
You
Yeah.
approach the light speed?
No. The gravitational redshift.
Oh, I think slower.
Slower. I think slower when the gravity is stronger. Yeah. Okay. I can't quite remember. I think it goes slower when the gravity is stronger. So actually, gravity here is a bit weaker than gravity here, right? Only very small amount, right? But these clocks can start to measure it like on a meter. You can start to measure that the time is actually going a little bit, I think, a bit faster, slow. Okay. Let's say it's faster here, slower here. You can actually start to measure that the time is actually slower over only a 1 meter height difference.
Yeah, I think it's slower on the.
Okay, slow on the.
I think Hawking had a joke about this. So we travel the plane, the time is slower, and you live longer. But the food on the plane is so bad, makes you also live shorter. So
All right. Okay. Right. Yes. So anyway, the point is that the clocks are getting, that accurate. We can measure time so accurately. It's like one of the kind of the most accurate measurements that you can actually do. Right? Okay. Right. Okay, so the previous years I did I had clickers where you log in to your phone and do multiple choice like this, but I don't think I'll do it this year. It's tedious after. It's fun like the first time, and then it's tedious for the rest of the semester. So I'm just going to do it the analog way. So, all right. So can you just do this one, and I'll give you a minute to work out that one, this question. I better work it out myself. Okay, you got something? Who thinks A? Who thinks B? C? D? Okay, all right. Yeah, that's what I get as well. I get 3.058 micrometers per second. So just simply 3.7 over 3.7 meters in 14 days. So 1 day is 24 hours, 24 times 60 times 60 seconds. And then micrometers is, to convert micrometers from meters, you need to multiply by a factor of 1 million. Right? Okay. Alrighty. Right, mass. So finally we're talking about the definition of mass. So, how do you define a kilogram? Now, I've been saying how getting like a physical standard like that, you get that rod of platinum, iridium, alloy, and then you say that that's your definition of a meter, how that's not a very good definition for reasons of, it changes, what if it's a hot day, blah, blah. Also, nobody has access to it. So you may be surprised to hear that that is still basically how you define the kilogram. And you might think, well, wow, surely there's a better way of defining the kilogram than just having some block of some object stored near Paris again, so it's near Paris. But people have found trouble trying to find alternatives to this because it should be more accurate, right? So it should be something that has higher kind of accuracy level in terms of variation. So the thing with defining mass is that it doesn't really depend so much upon anything like temperature. So it doesn't matter that this is going to heat up. Unlike length, where on a hot day the rod is going to be a bit longer or shorter. This thing, it doesn't matter so much that it's heated up or anything. The mass would still remain the same. Maybe the only problem would be that over time, if people are picking it up, obviously this is why they don't allow anybody to really pick it up or put their dirty little finger marks on it. Of course, that's going to mess up the definition a lot. So, but of course, you got to use it, right? You can't just have this pristine block that you say, okay, this is the 1 kilogram mass, but nobody can touch it or do anything with it. Otherwise, it'll mess up our, precious definition of the kilogram. And so let's not touch it or do anything. And, you also need to use it, right? You need to have basically the equivalent of the 1 meter sticks around Paris. So the kind of thing that they would do is they would get replicas of this, right? This is the master kilogram. And then you would get your, copy of the kilogram. So you just, put it on some, you get something to measure the same mass. And then you very carefully take it back to your country, and then you've got your copy of the kilogram there. So, it turns out it's really quite hard to define alternatives, and so people have been trying very hard to do this. And the kind of levels of accuracy that we're talking about are so this is only accurate in 1 part in 10 to the power of 8. 10 to the power of 8 is 100 million, right? So the fractional error is about 1 in 100 million. That's like way less accurate than, for example, the clocks. The clocks were very good, right? The clocks were something like 1 part in, so 1 over 10 to the most modern ones are 10 to the 18, right? So this is 1 second in something like the age of the universe type of accuracy. This is only 1 part in 10 to the 8. So it's really, it's surprisingly hard to define a kilogram in a very consistent way. So this is what people are trying these days. So what you could do, so there's two kind of different strategies here. So the first one are these silicon boules. So what you can do, so you might know that So 1 mole of carbon 12 is, of course, 12 grams, right? It's actually definition, right? So, okay, in the end, we're not going to use carbon, but the idea is the same. So if we get, Avogadro's number of Avogadro's number of these atoms, then that would be 12 grams, right? I mean, we defined 1 mole of carbon 12 to be 12 grams. So we just have to get that many atoms, right? Then the problem is, okay, so how are you going to make something with exactly that number of atoms? This is it's a heck of a lot of atoms, and you're going to have to, like, what are you going to do? Count them? I mean, it's going to be pretty much impossible to just atom by atom make some object with exactly that number of atoms, and of course you're going to probably lose some atoms in the process. But that's the basic idea of this. So instead of using carbon, we can also use silicon because silicon is also, so it's not defined to be 12 exactly, it's defined to be some other number, but it doesn't matter, it's just so long that we've got our fixed definition. And then what this guy's trying to do here is to make like the most spherical object ever made in human history. And so if you make it like perfectly spherical, right, has some radius, then silicon has, some sort of fixed crystalline structure. What is it actually? Is it, what's the crystal structure of silicon? I can't remember right now. Anyway, it has some particular crystal structure, right? So that, okay, I don't know. But let's say it's cubic just for now. So we know like the atomic distance between these atoms. That's it's very regular. It's a crystalline structure. So you know the how many atoms there are going to be in a particular volume. Okay, and then our job is simply to make some volume, which is just 4/3 pi r cubed, in the most accurate way possible. So long as we've got our volume right, then we know like the crystalline structure of silicon, and one of these, say, one of these cubes has, say, 8 atoms. We know the volume of this cube. It's just a cubed. The volume of this is a cubed, and in each cube there's going to be 8 atoms, but actually some of the atoms are shared between other cubes, so effectively I think there is 2 atoms per cube, okay? And then if you just divide by the volume and then there's 2 atoms per cube, then you can get exactly, well, hopefully exactly the, this many atoms. That's basically the strategy of this, and I think, so the game is to just make like the best ball ever made in human history. Okay, so that's strategy number 1. The second strategy, this contraption, is essentially this is just a sort of a fancy scale. So it's just a kind of a fancy scale. So we've got some weight here, and you can just think of that as being some. Well, it's a scale, but what it does is to provide some force. So force at the mass is mg down, provides a force, and you have some power supply, and you can relate like how much electrical energy you need in order to provide that force. So it's basically something that converts your force into an electrical measurement. And electrical measurements, we've got reasonable ways of actually measuring that too. So basically converting your mass problem into an electrical problem, and then once you've got an electrical problem, then use your electrical standards, which are a bit better than the mass one. Okay, I think that's the last slide, right? Oh, okay. We'll follow this up next lecture. Okay, so that's all for today. See you on Thursday.